In this lecture, we'll continue our discussion of graph theory and how it's used for Bayesian methods, but in particular, we'll look at how graphical methods can be used to visualize probabilistic models. So we will look first at why graphs are useful for visualizing probabilistic models and some of the methods to create them, and then we'll look at some examples of how they're used. So the biggest motivation for graphical models as visualization techniques is that they allow us to visualize a difficult problem and all of its components in a very useful way. They, in particular, make these complex relationships that we find in a lot of the probabilistic models that we create much easier to understand. There are automatic generators of graphical models that are available, and one example of that is GraphViz. You can use this to actually create automatically a graphical representation of a model. You start by specifying what the model is, and it'll produce the graphical visualization as a result. Some of the characteristics of these kinds of techniques, either automatic or manual, they use plates, and we'll see examples of the plates within the model to represent multiple nodes. This is better than writing out a lot of nodes. You can use a plate to represent repeated nodes. When the automatic techniques are used, it sometimes is the case that they don't represent all the variables very well. For example, predictor variables and regression sometimes aren't represented so well. All right, so let's look at some examples of graphical displays. The first one we'll look at is a regression example. Suppose we've got SAT scores in school districts, and we think that these SAT scores are distributed by a t-distribution with parameters nu for degrees of freedom, mu for the center location for the distribution, and sigma for the scale. We'll let each one of them have a prior distribution, so we'll let nu be exponential with parameter lambda. We'll let mu be a Gaussian with parameters mu naught and kappa for its precision, and we'll let sigma be a gamma with parameters scale and rate S and R. For predictor variables, we'll use x1 for the amount of spending in a school district and x2 for the number of students who take the test in a school district, or rather the percent of students who take the test in a school district. Now the regression model has parameters beta naught, beta 1, and beta 2, for beta naught being for the intercept term and beta 1 and beta 2 being on the predictors. So we're going to let beta naught have its own Gaussian distribution with omega naught and tau naught being, omega naught being its mean and tau naught being its precision. And the two parameters on the predictors are going to have a common Gaussian distribution, which will have a mean of omega and a precision of tau. Okay, with those specifications, then we can run GraphViz, and it'll generate a model like this, which is almost complete, but it's missing a lot of things. It doesn't show the actual parameters in any of the prior distributions, and it also has left out the mu parameter and its prior distribution for the student t. But you can see it does have the sigma for the student t, which is a gamma. It has the nu, which is exponential. It has the beta naught, which is a Gaussian, and it notice that it's using a plate here to show that there are two of these beta j's, and they both are Gaussian. And then it's showing the plate around the likelihood that there are 50 students that are being modeled in this particular case. So GraphViz is convenient. It's something you can use in your Jupyter notebooks, but it does have its issues in that it leaves things out and it's not as complete as we'd like. Let's look at another example, and we'll see how to do a manual graph, and it gives us a little more complete display. So in this example, it's a classification example. We're going to make it a little complicated to show the power of these graphical displays. So we're going to let y sub is be the response of a subject, for instance, a rodent, where s is the number 1 through n of these subjects. on a drug in a test. So we're going to test them, and each rodent will be tested up to m times. And we're going to let theta sub s be the probability of a positive response by the subject. So this is our typical Bernoulli trial, and we're going to have a number of Bernoulli trials then. We'll let the prior for theta sub s be a beta distribution, but we're going to reparameterize it in terms of omega and kappa, where omega is actually the mean of the beta distribution, and kappa is roughly a measure of how many observations go into it. And it's really a nice way to parameterize, because kappa basically allows us to say how strongly we believe the effect of the beta distribution, in particular its mean, is on the theta in this case. So the bigger kappa is, the more we think the beta distribution defines the theta. And the lower it is, the less we think it defines. In alpha, the parameters in the beta distribution that we normally use, alpha can be defined as just omega times kappa, and beta is 1 minus omega times kappa. Okay, and we're going to make this a little bit more complicated in what's called a hierarchical model, which we will be talking about later in the course, in that we're going to put a prior distribution on the parameters of the beta, the prior for the probability of a positive response. So on the omega parameter, we're going to put a beta with parameters A and B, and on the kappa, we'll put a gamma, since it has to be non-negative, with parameters S and R for scale and rate. And this is the graphical depiction of this model. And you can see that we can represent the model in a convenient way to show the relationships that are occurring between the different parameters and variables in the model. If you start at the bottom, you'll see that there's our response. It's a Bernoulli response. We have a number of trials, the I counts that, and we have the subject. And then on top of the parameter for this Bernoulli, the theta, we have a beta. This is our prior for the theta parameters, a beta. And as we said, we parameterize it with omega and kappa. And those are shown there by that beta distribution. And that in turn is parameterized respectively. The omegas are parameterized by another beta with parameters A and B, and the kappa is parameterized with a gamma with parameters S and R. So this very nicely illustrates our problem as we've defined it and how we've arranged the probabilistic structure within the problem. This is called a Kruskal diagram, after the gentleman who came up with this way of representing it in a textbook that he has. And it's a very popular way to represent Bayesian problems. There are templates for it that are available. If you use LaTeX, you can generate these things automatically and put them in your papers using LaTeX. So it's a very convenient and nice way to represent it, but it is a manual process. You actually have to enter the things in. You can also create this, obviously, in any kind of graphing software that you use. You can create your own version of these kinds of things. So hopefully this has given you a sense of how we use graphical models to show the internal structure of Bayesian models and the relationship between the different parameters and the likelihood and the priors that we have within the models.